So I'm going to tell you kind of a different perspective, a different Gröbner degeneration, and some of the related combinatorics. And so this is joint work with Zach Hamaker and Oliver Pechenik. So maybe you can feel free. I'll keep an eye on the chat as we go, but maybe they can help me field some questions in the chat as well. Okay, so yeah. So first of all, I'm going to start by telling you about Schubert varieties and some things about the flag variety and the cohomology ring associated to the flag variety. And next, I'll review this Gröbner geometry story of Knudsen and Miller. And then I'm going to tell you about these newer combinatorial objects called Bumpass pipedreams and why I think they also play an important role in the Gröbner geometry of Schubert varieties. Okay, so starting off with Schubert varieties, there's this complete flag variety, which you can think about as the quotient of the general linear group by the Borel subgroup of upper triangular matrices. And so there's a natural action of this Borel by just left multiplication, and the orbits that you get out of this action are called Schubert cells, and they give rise to this Bruja decomposition, which is a cell decomposition of the flag variety. And so there's one Schubert cell for each permutation in the symmetric group. And then you can take the closures of these cells to get things called Schubert varieties. And the Schubert varieties, they give rise to Schubert classes in the cohomology ring. And the Schubert classes are super nice in that they form a linear basis for this cohomology ring. So if you want to understand the structure of the ring, you really want to say, well, how can I multiply two of these Schubert classes and expand the product in the Schubert basis? And so a key goal in Schubert calculus is to understand this product structure and to get a handle on the combinatorics that's associated to it. Okay, so if you don't want to think in terms of, say, cup products of classes in cohomology, there's good news for you. Borel defined an isomorphism that takes the cohomology of the complete flag variety to a quotient of a polynomial ring. And so you just have a polynomial ring in n variables, and you mod out by this ideal that's generated by non-constant elementary symmetric polynomials. And so there's lots of potential choices you could make to represent one of these cosets in this quotient. But a kind of natural question to ask is, what's a good polynomial representative for this quotient? Good is very vague. Lots of people might have different ideas of what good should mean. But one answer proposed by Lascaux and Schutzenberger was the Schubert polynomials. Okay, so Schubert polynomials, they have kind of this algebraic recursive definition. So you start...
Before you go, you continue, there is a question. Is B
yes.
Diagonal matrices?
So B are, thank you, Colleen got it for me, but B are the upper triangular matrices. But later, diagonal matrices are going to make a very important appearance, and I'll denote those with T for the torus of diagonal invertible matrices. Yeah.
Okay, thank you.
Okay, so to define these Schubert polynomials, there's just an algebraic definition. And so you can start from the longest permutation in the symmetric group. And this is this permutation in one-line notation where the whole string is reversed, this W naught that you see here. And then the Schubert polynomial is just this monomial here. And then you get the rest by applying these divided difference operators. So I'm not going to go much into the details for time, but just it's this very like recursive thing that you just kind of keep hitting these polynomials with these operators whenever you see a descent in your permutation. And you're essentially working your way down in weak Bruja order from the top all the way down to the identity where the Schubert polynomial is just 1. There's also doubled versions of these, which they're defined by the same operators acting on the x's, but then they have a different initial condition. So it's double in that there's twice as many variables. You now have x's and y's floating around, but you can get back to the single versions just by plugging in zeros wherever you see y's. So this is kind of the initial perspective that Lascaux, Schutz, and Berger had. But since there's been many combinatorial ways of thinking about these polynomials as well. Okay, so how natural is this choice? Well, combinatorialists could argue that this choice is natural in the sense that these polynomials have a lot of nice properties. For instance, if you expand them out in the monomial basis, you get a positive integral expansion. So these coefficients are positive integers. They're also stable. So when you include one symmetric group into the next by just kind of appending another number to the end of a permutation in one line notation, the Schubert polynomial stays the same. And then if you want to compute in this cohomology ring, if you want to take cup products of Schubert classes, the coefficients that you see over here are the same as the coefficients you would see multiplying Schubert polynomials and expanding them out in the Schubert basis. So you get all of these coefficients by looking at the Schubert expansion over here. So a priori, things could be kind of up to this ideal modulo, the ideal of elementary generated by non-constant elementary symmetric polynomials, but you don't really have to worry about that. You can just kind of multiply Schubert polynomials upstairs as you will. I mentioned this last thing just because there's a lot of people here who probably like symmetric functions. So every Schur polynomial is actually a Schubert polynomial indexed by some Grassmannian permutation. So if you study Schur polynomials, you're at least very familiar with some Schubert polynomials. So yeah, and then I had mentioned combinatorialists like these. There's a ton of combinatorial formulas. I'm just going to mention one for now of Fomin Krylov and Bergeron-Billy in terms of these sort of planar histories called pipe dreams. And so the double Schubert polynomial can be represented as a weighted sum over pipe dreams. I'm not going to formally define them for today. Some of you have probably met them before, but if you haven't, feel free to ask me for more information at the break. But what I want you to take away from this picture right now is that you weight these objects by looking at where the crossings happen. And then, for instance, there's a crossing in row 1 and column 1. So that's this binomial x1 minus y1. And there's a crossing in this diagram in row 3 and column 1. So that's giving you this x3 minus y1. And then you just take a product over all the crossings of these binomials. And so here I've listed out all the pipe dreams for the permutation 2, 1, 4, 3. And so you just add these different weights for every pipe dream that you see. So this was fast. I just want you to get kind of a flavor of what this formula looks like. But yeah, so combinatorialists like studying Schubert polynomials, but the geometers still might complain that it's still a choice. They would be perfectly happy just multiplying Schubert classes in the original cohomology ring of the complete flag variety. Why do you need to make this choice of polynomial? And so there's one argument for the geometric naturality of these polynomials due to Fulton. Fulton expressed certain Chern class formulas for degeneracy loci in terms of double Schubert polynomials. And then later, Knudsen and Miller kind of built up on this idea and created a theory around Gröbner geometry to really canonically identify Schubert polynomials as the right coset representatives for these Schubert classes under the Borel isomorphism. So I'm going to, in the next section, unpack that idea a little bit more and explain this Gröbner geometry story. Okay, so Gröbner geometry. So our story starts with these things called matrix Schubert varieties. So you can define them in terms of these natural projections of the general linear group onto the complete flag variety and an inclusion of the general linear group into the space of n by n matrices. And so very just kind of formally, you can define the matrix Schubert variety as the closure of the inclusion of the pullback of the Schubert variety from the complete flag variety. So you take the Schubert variety, you pull it back along this projection map, you include it into the space of n by n matrices, take the closure, and you get some algebraic variety. So there's also more concrete ways of defining this in terms of certain rank conditions on northwest submatrices of this locus of matrices in the space of n by n matrices. There's also a corresponding Schubert determinantal ideal, and Fulton gave a very explicit, nice generating set that sort of generalizes the ideas of determinantal ideals. And so this Schubert determinantal ideal, it's prime. So not only are these generators set theoretic, but they're describing this scheme theoretic behavior. And also, indeed, the matrix Schubert variety is the vanishing locus of this ideal. So I'm not going to get into the coordinates and everything of this. I'll again kind of show you examples later. But this definition is maybe abstract, but it's a solid definition. Okay, so here's just kind of a picture to keep in mind. Again, with our running example 2143, the matrix Schubert variety, it's defined by this locus of 4 by 4 matrices where the top entry is just 0, its rank is 0. And then this 3 by 3 matrix has rank at most 2. And it has a corresponding Schubert determinantal ideal where you say, well, Z11 has to vanish, and this 3 by 3 matrix has to vanish. Okay. So yeah, what we're going to do now is figure out how to associate a canonical polynomial to a matrix Schubert variety. And so we have this group of pairs of invertible diagonal matrices acting on the space of n by n matrices by sort of almost conjugation. So T acts on the left by multiplication, U acts on the right, but we twist it with an inverse so that it's a good left action. And this turns the coordinate ring of the space of n by n matrices into a Z2n graded ring. And so a multi-degree, this isn't really a definition, but just an idea of what this gadget is. It's a way of taking a graded module over this coordinate ring to a polynomial in x's and y's. And so whenever in particular you have a subvariety of this matrix space that's stable under this torus action, its coordinate ring is a Z2n graded module. And so you can talk about the multi-degree of that variety. And so it's the theorem of Knudsen and Miller that the multi-degree of the matrix Schubert variety is actually the double Schubert polynomial. And so they identified this matrix Schubert variety. They showed that its multi-degree is the double Schubert polynomial. And this also in turn let them recover the earlier fact that, say, the single Schubert polynomial is a representative, the coset representative for the Schubert class under this Borel isomorphism. And you can also talk more generally about, say, Borel equivariant cohomology down on the flag variety, and this double Schubert polynomial is telling you about that. Okay. So how do we actually compute this thing? There's sort of a recipe that's characterized by 3 axioms. And so normalization basically says that multi-degrees of coordinate subspaces are easy. We're just going to take a product of binomials over the variables that we zero out to form that coordinate subspace. And then additivity says if we have a possibly scheme theoretic union of algebraic varieties, then the multi-degree is just going to be what we get by adding over the top dimensional components, paying attention to the multiplicity of that set theoretic component in your algebraic variety, or in your scheme. And then the third property, which is really useful, is that multi-degrees are preserved by nice enough degenerations. So I'm not going to make nice enough precise, but I'll tell you one sort of nice enough degeneration. Okay, so a Gröbner degeneration is one of these nice enough degenerations. And so what we can do is we can fix a monomial term order on our coordinate ring. So a way of saying this monomial is stronger than this one and breaking ties between them. And so if we look at a polynomial in our ring, the initial term is just going to be the term corresponding to the monomial that wins under this term order. And then we can take an initial ideal of any old ideal. We can take its initial ideal is going to be the ideal generated by all. Oh, sorry, I'm seeing in the chat, each of the xi's, yeah, they are, say, irreducible components in this scheme theoretic union. Okay, so yeah, with this Gröbner degeneration, the initial ideal is going to be generated by the lead terms of all the elements of our ideal. And that might seem overwhelming because the ideal has a lot of generator or a lot of elements. But what we can do is take a distinguished subset of the ideal. And if the lead terms of that subset generate the initial ideal, then we call that subset a Gröbner basis. And it's a fact that finite Gröbner bases exist. And Buchberger's algorithm gives an explicit way of generating these finite Gröbner bases, starting with a generating set of your ideal. So it's something that computers, at least for small examples, can just turn out for you, but maybe gets computationally hairy as the number of variables grows. Okay, so here's just a toy example. We can take this Schubert determinantal ideal and degenerate with respect to an anti-diagonal term order. So this means if we look at any matrix minor of our generic matrix, the lead term of that matrix minor is going to be the product of the anti-diagonal terms. So here, for instance, we see these anti-diagonal terms, and this corresponds to this generator here. So it's a fact that this Schubert determinantal ideal is the Fulton generators are a Gröbner basis for this ideal. And then kind of the recipe is we can take the prime decomposition of the initial ideal, and you'll notice that sort of prime by prime, what we see is a correspondence with the pipe dreams here. So this Z11 and Z31 tells you that you have a crossing tile in position 1,1 and position 3,1. And so this isn't just a fluke about 2, 1, 4, 3. Thanks to Knudsen and Miller, we know that this always happens. So kind of the magic of their Gröbner geometry story is they show that for any anti-diagonal term order, Fulton's generators are a Gröbner basis. And not only that, but the initial scheme that we see, its coordinate subspaces are indexed by pipe dreams for the permutation. And so you can take your matrix Schubert variety, degenerate, you get this union of coordinate subspaces that are on the nose labeled by pipe dreams. And so this Gröbner geometry story, it also explains things like the positivity and of the monomials in, say, the single Schubert. Yeah, I'm seeing a question. Yeah. Is it always true that the Gröbner bases are Fulton except on the last example? In the last example, this is the generating set given by Fulton. And it's true that the generating set given by Fulton is Gröbner for any anti-diagonal term order. Yeah, that's what Knudsen and Miller said. Here, I'm technically only giving generators coming from the essential set, but you could have too many generators, or you could have a better generating set defined by Fulton. Yeah.
Also, Anna, you just have 5 more minutes.
Okay. So yeah, what about diagonal term orders? So if I look at, the first term order I would think of would not be an anti-diagonal term order. It would be like just where I kind of read along the rows of the matrices how I would read any old book, like left to right and then working down. So anti-diagonal seems a little strange, even though the combinatorics works so beautifully and so perfectly. So Knudsen, Miller, and Young, they showed that Fulton's generators are Gröbner under a diagonal term order, if and only if your permutation is vexillary. So outside of the vexillary setting, things start to get hairy. The limit might actually fail to be reduced. You won't be seeing square free monomial ideals. So it gets a little discouraging. But in the vexillary case, they give an analogous Gröbner basis sort of result where you see the coordinate subspaces being reduced in the limit and labeled by, say, flagged tableau. So there's an analogous story there, but outside of vexillary, not much was known. And I would argue that it was kind of difficult because they weren't looking at the right combinatorics. They were only seeing a shadow of it through these flagged tableau. And so in the time that I have remaining, I'm going to try to tell you a little bit about what the right combinatorics should be. So I'm going slower than I thought. So a Bumpass pipedream, it's this combinatorial object that's built out of sort of 6 tiles like this, forming kind of a planar network. So it has to satisfy some rules. I'll just show you, here's an example, and this is a non-example. You can't have pipes just kind of giving up in the middle or crossing multiple times or starting or ending at the left and the top. So you can associate a permutation to a Bumpass pipedream by just kind of tracing where the pipes end up. And you can look at all of the Bumpass pipedreams which correspond to a certain permutation. And so the theorem of Lamley-Chamizono is that the double Schubert polynomial can be expressed as a weighted sum over Bumpass pipedreams. So here the weighting is happening now not by looking at crossing tiles, but looking at blank tiles. So this, to people who have studied Schubert polynomials for a long time, is kind of intriguing because these 2 different formulas, by summing over these squiggles, look very different term by term, expressed as sums of products of binomials. So it was a little bit surprising that there's this new different looking formula. So it actually appeared, but hidden in disguise in this older preprint of Lascaux. So if you want more information about this connection to ice, you can check out a preprint of mine, Bumpass pipedreams and alternating sign matrices, explaining how you can rederive this Lamley-Chamizono formula from older work of Lascaux. But he didn't draw the squiggles. He wrote, say, alternating sign matrices and configurations of the 6-vertex model. Let's see, I'm going to, for the sake of time, skip to this example, 2143. So this is the first non-vexillary permutation. And you'll notice that if we now degenerate with respect to a diagonal term order, we see kind of Bumpass pipedream by Bumpass pipedream, a connection with the primes that we're intersecting here. So it's it looks just like the diagonal or the anti-diagonal degeneration in terms of this combinatorics corresponding to primes sort of thing. So the conjecture in joint work with Zach Hamaker and Oliver Pechenik is that if you take a degeneration of a matrix Schubert variety with respect to a diagonal term order, you see the components and the degeneration labeled with the correct multiplicity by Bumpass pipedreams. So Bumpass pipedreams tell you what components show up with what multiplicity. So even though the degeneration is no longer reduced, it's conjecturally telling you what this looks like. And so we have some partial results in this direction. So we define a different generating set and show that sometimes these generators are Gröbner for special classes of permutations. And then we're able to kind of build up through block sums of understood permutations where the conjecture holds to come up with a class of permutations where we know the conjecture works. But outside of this class of permutations, it's very open. Is the diagonal Gröbner geometry really described by Bumpass pipedreams? So I think it is, but there's a lot more work to do. So with that, I'll go ahead and stop. There's references, and thank you so much.
Thank you. So let me pull up the chat. And Sam is asking any connection between the appearance of ASMs here and the McNeil compilation of a strong Brucher order.
Yeah, no, I find it funny that in this story, alternating sign matrices appear in kind of two ways. It's a little bit strange to me, but maybe alternating sign matrices are just kind of ubiquitous in combinatorics. But you can talk about like a generalization of matrix Schubert varieties, and alternating sign matrices are telling you kind of exactly what sorts of sub-varieties of matrix space are carved out by these at most northwest rank conditions. But there will be one for each alternating sign matrix, but they're no longer irreducible. But as to like formula by formula, I don't know, maybe it's a fluke or maybe there's something cool there.
Let me see, because there are many around.
So I'm seeing, does this degeneration depend on the choice of diagonal term order? So yeah, when you have things that aren't reduced, you can get different limits based off of your diagonal term order. And so the idea of the conjecture is that maybe you don't know exactly what the limit looks like, but you know set theoretically up to multiplicity how many times each of these set theoretic components is showing up. But yeah, the actual degeneration, since it's not reduced, now does depend on which diagonal term order.
And do you have any description of Banner permutations, such as like pattern avoidance or something like that?
So I'm not sure about pattern avoidance for Banner permutations, but there was this class that I kind of brushed by, CDG permutations. So certain modifications of Fulton's generators. It seems conjecturally like there's some pattern condition describing when things are CDG, meaning these CDG generators are a diagonal Gröbner basis. We have the list of patterns in our paper on the archive, but we haven't proved that things are actually CDG when they avoid that list of patterns.
Okay, one more. How does the multiplicity of the component get encoded in the pipedream?
Yeah, this was another slide I kind of blew by. So a strange thing about bumpless pipe dreams is that you can have multiple bumpless pipe dreams with the same set of blank tiles for the same permutation. This is very different from pipe dreams, where each pipe dream is uniquely determined by where its crossing tiles are. So here you can actually have a whole zoo of bumpless pipe dreams with the exact same set of blank tiles. So when you have two different pipe dreams for the same permutation with the same blank tiles, conjecturally this means that component, that linear subspace zeroed out by, or that coordinate subspace zeroed out by these variables is appearing with multiplicity by counting the number of pipe dreams for that permutation with that underlying set of blank tiles.
Okay, what a satisfying explanation for multiplicity. And I'm gonna, there is no question about it, but I'm gonna ask it, what about quantum?
Oh, yeah, I don't know. Even the K-theory, there's work to do to think about what K polynomials of these degenerations, especially when things aren't reduced, look like. Yeah. And things like from the Knudsen-Miller story, or Knudsen-Miller story, things like subword complexes, and interpreting them. When do these things have subword complex structures? There's just a whole lot to do. Yeah.